Julia and I were asked to sort of lead, I'm going to give a formal talk, and then we're going to sort of put up some questions we have at the end, and then in the next session we'll be breaking up into groups. Either some of the questions we raised or questions from the audience. So as I'm going through, if you can think up some questions that you might want to raise, or general questions for a broader discussion, we'll put them up at the end. And I also want to keep it, very informal. If you have some question when I'm going through this, and stop me. So I was asked, or we were asked, to talk about electromagnetic observables during mass transfer across wavelengths and timescales. And I know this is a workshop on stable mass transfer, but I'm going to talk about things that can happen during unstable mass transfer as well. And I'm going to be a little bit provocative. I think I'm going to talk about a lot of things that you may not normally associate with mass transfer, that you may not appreciate could be related to mass transfer events. Things like fast radio bursts and fast blue optical transients. You may not have heard of the Blue Ring Nebula, so I hope to try to go through these. And I'm also going to switch between sort of massive star considerations involving compact objects accreting, and some things that I think are more broadly relevant also to lower mass binary interactions. So as we've heard in this talk, if you want to go from a massive star binary to a gravitational wave source, for example, or many of the other exciting things that happen along the way, you have a number of different phases of mass transfer onto the compact object or into the compact companion. And this can occur on a variety of timescales, from nuclear being the longest, the thermal timescales, and possibly even dynamical timescales. So when we talk about dynamical unstable mass transfer, it's not like that happens immediately. It could at least take a few orbits. So you can have very brief phases of mass transfer that in principle could produce something detectable prior to even some kind of dynamical phase like a common envelope. And of course, if you have these mass transfer rates onto a compact object, they represent a range of accretion rates from sort of, Warner Eddington or up to things that are super, or even what I'll call hyper Eddington accretion rates. But they may be very short-lived phases, so they may not appear in the local population of events, but they're nevertheless occurring out there in the universe. And exactly our partition, say, between thermal and dynamical time will depend on some of the questions that we're addressing in this workshop. So I just want to go over from a theoretical standpoint a few aspects when you do have super Eddington accretion onto a compact object. I think a generic feature is that you get very powerful outflows from the disk, winds from the disk or jets, and sometimes these are interchanged. And one essential feature is if you're accreting at a sufficiently high rate, basically photons are trapped in the accretion flow, so it cannot cool. And when it cannot cool, the energy that's liberated gravitationally as matter falls into the potential well cannot be radiated, obviously. And so what simulations show is that a large fraction of it actually comes out in outflows. And so if you feed the outer edge of some accretion disk at some rate R out, actually what makes it down to the compact object can be a small fraction of that, which tends to, theoretical models tend to say is some power law in the inner to outer radius. And we know that these disk outflows / jets can power sort of large scale nebula. I'll come to this in a second. Microquasars. It may be responsible for beaming the X-ray emission in these systems, which may or may not be intrinsically super Eddington, but certainly in some cases appears super Eddington. And then also, as we've discussed, if you have a sufficiently high mass transfer rate, you can get mass loss out of L2, which may produce a large, extended, possibly dusty disk that could produce an infrared excess. And of course, we see these wind-inflated ULX bubbles in other galaxies. These are highly accreting sources in our own galaxy. The prototype we've already talked about is SS433 with the Manatee Nebula, where you have some kind of evolved donor star accreting probably onto a black hole. There's all types of phenomenology. You see this sort of big, large-scale, multi-parsec, maybe even hundreds of parsec nebula that are basically inflated bubbles by the winds from the accretion disk. On smaller scales, you can see radio emission from what appears to be a processing radio jet. You see these lobes where the jets go out and shock the swept up interstellar medium material, producing hot spots in X-rays and in non-thermal radio waves. So there's a really deep rich phenomenology of these systems, which in these cases, extend across multiple. This is why it's called the manatee. It looks like a manatee. This is from my student Naveen. So another feature, interesting feature, I think, of these systems is that the the accretion disk can precess, for example, as a result of lens tearing precession about the spin axis through a black hole, and this may be responsible for causing these ULX sources to swing in and out of our line of sight, and you can measure these superorbital periods. So I want to connect now to some other observed phenomenon in astrophysics, which I speculate with my student might be related to these sources. And these are fast radio bursts. We all know what fast radio bursts are. But essentially, there's been a discovery of one of the most studied fast radio bursts that shows that the arrival phases of the burst are periodic. So every 16 days, the FRBs only arrive in these few-day windows every 16 days, and you see some actual structure in the properties of the fast radio burst across this few-day window. And we're also, learning that, and so it's sort of been suspected that all FRBs arise from magnetars. It's not exactly clear how a magnetar would produce this type of periodicity. And we also now have evidence that some fast radio bursts occur in old stellar populations like globular clusters, where it may not be so trivial to make young magnetars. And so this gets people thinking: is there something going on in terms of binary evolution that could be related to fast radio bursts? I should say my review is highly biased towards things I've been thinking about. But so I think one of the interesting things is whether you could get periodicity from an X-ray, a binary, for example, an accreting neutron star or black hole. And as I said, because of this lens tearing precession effect, you predict some connection between the orbital period of the binary, which is basically how big the accretion disk is and how long it takes for the jet to precess. And these are sort of known ULX systems. They exhibit this kind of behavior. And sort of it's interesting that the precession periods are similar to the claimed periodicity times in a few FRBs. And so the picture, without going into any details, since this is not the right conference for this, is that you may get shocks or reconnection in plasmoids that are ejected along the spin axis of the black hole, and this could potentially produce FRBs that you only observe when the jet is pointing towards you. So it's interesting to think, as we look at populations of fast radio bursts, what types of galaxies they happen in. Is there any connection to where we might be getting phases of super Eddington accretion, which you kind of need in these scenarios to get a powerful jet to observe something? Another interesting connection to FRBs, I think, is the fact that many of these repeating sources exhibit these compact radio nebula. So there's 3 FRB sources now, and sitting at the location where the FRBs are coming are these very radioluminous. They're brightest non-nuclear radio sources we know about, very compact, less than a parsec in size. And we also know that they're highly magnetized, not only because they produce very bright non-thermal synchrotron radiation, but because we see a high rotation measure, which tells us that this medium is baryon rich. So it's just a pulsar wave nebula would not be baryon rich, it would be electron-positron pairs. But the fact that it's baryon rich is suggestive, okay, maybe there is some baryonic matter, for example, mass transferred material in these nebula. These are far more luminous than the radio sources I showed you, for example, from SS433, which are a few orders of magnitude dimmer. On the other hand, we know sources like SS433 are long-lived systems, 10 to the 5, 10 to the 6 years. So we hypothesized, well, what if you had very much younger mass transferring sources, very short-lived mass transferring sources? Could that explain these very compact but nevertheless much brighter radio nebula? And so with my student Naveen, we worked on these sort of inflated hypernebula models where we basically consider a model where the outflows from the accretion disk are inflating this bubble. So we're tracking the properties of the expanding bubble. And then we're assuming the jet goes out and shocks and injects relativistic electrons. And then we follow those electrons as they cool through radiation and expansion and follow the synchrotron radiation they produce. So you can essentially predict, given a mass transfer rate and how long you think that mass transfer rate should exist and the power of the jet, you can predict things like what should be the time-dependent size of the nebula, what should be its synchrotron emission, and things like rotation measure, which you can compare to observations. So this is just showing this type of model in greater detail. So this is an example on the right showing the number of particles you inject into the nebula, the magnetic field strength, et cetera. And so typically what we find is, you can get actually if you have sufficiently short phases of very high mass accretion rates, such as we might get in thermal timescale mass transfer, or maybe even pre-common envelope dynamical mass transfer phases, you could actually get quite bright radio nebula that might, instead of extending hundreds of parsecs in size, might be less than a parsec in size because they're very young. So this is just showing some light curves for different assumptions about how long. So transferring the same amount of mass onto a black hole companion for different amounts of time, what type of radio light curves these nebula would have. And so you can ask questions like, okay, this should produce actually thousands of Milijansky radio sources across the sky, potentially, depending on how frequently we think these mass transfer phases happen. But they could be so you can go through and ask, for example, the Very Large Array Sky Survey, how many of these mass transferring compact hypernebula might exist in the survey, and we find it could be substantial, but only a fraction of these will actually exhibit time variability over the course of a survey. Otherwise, they would just basically be stationary, temporally stationary sources. But anyways, it gets you thinking about whether we could actually go out and look for these short-lived phases of very rare mass transfer. I want to now switch topics and talk a little bit about things that apply to all stellar mergers. In fact, most of the ones I'll be talking about are lower mass stars. These are we've heard about this luminous red nova, whether they are luminous or red, I guess is somewhat debatable, depends on what phase you look at them. But this is a number of the luminous red nova sort of light curves. And these are the samples. There's slightly over a dozen of these now. And we compiled them in this paper with Tatsuya. There's a few aspects I want to point out about the light curves of these, and we'll get to why we know that they're from stellar mergers in a little bit. But basically, there's two peaks to the light curve. So there's an early peak sort of at the very beginning. Actually, there's a pre-dynamical rise in many of these, which is suggesting of some mass transfer happening before the final dynamical plunge. But then there's a first peak, and there's a second peak in the light curves. And this actually, I'll come back to this in 1 second. But the other thing I want to say is that, in many cases, you can go back and look pre-imaging at the location of the luminous red nova and get a constraint on the progenitor system. And these are sort of the donor radii and assumed donor masses for a subset of these for which you're able to do that. You see that many of these luminous red nova, the stars are sort of mildly evolved or yellow supergiants. They're at the end of the main sequence or slightly beyond that. We're not seeing a lot of red giants or red supergiants in the progenitor samples. So these are stars that are presumably undergoing mass transfer as they're evolving up to the red giant branch and are merging. So I want to talk a little bit about how these light curves are determined to sort of give you some hint about what type of information you can get on them. So this is just an example of a simulation. I've done quite a bit on these as well. Of a common envelope event where you have a companion star which falls into the envelope of the accretor, of the donor. And to generalize grossly, it depends on what are the mass ratio of the system, et cetera. But to me, the rough outcome of this is during the plunge phase, some fraction of the outer envelope of the donor star gets basically stripped off and ejected into space. There'll be possibly further mass loss as the companion spirals in. But typically speaking, for some mass ratio that's not extreme, you might eject a few 10% of the envelope. And in that process of ejecting material, it's sort of heated up to a temperature which is of order the escape speed. And so when it re-expands, it'll acquire a kinetic energy which is comparable to the thermal energy deposited in the material. And actually, this is just to point out that, even prior to the dynamical plunge of the companion, you start to get mass loss, for example, from L2 that can sort of set the environment around which this final coalescence occurs. And so when you look at these, like a light curve of a supernova of any kind, what you're seeing first in the beginning of the light curve is the fastest outer material. And then as time goes on, you're seeing deeper and deeper in. Of course, this is grossly simplified since it's not a one-dimensional problem. But nevertheless, you can model it in a simple one-dimensional way. And what you find is that you naturally get these two peaks that we see in the luminous red light curve. Essentially, the first peak is the outermost ejecta layers, which acquire the highest speed. They have the highest thermal energy, and they radiate their energy quickly. But then as the photosphere retreats inwards, it reaches the point where hydrogen recombination sets the photosphere location, and then that proceeds inwards to the ejecta. And so the rest of it can in principle be powered by hydrogen recombination. And Hosh has pointed out this early in this game. So basically, by measuring, the point is by measuring in this early phase, you're learning something about the fastest material, and by measuring this, you're learning something about the bulk of the ejected material. What I want to say is that there are a lot of similarities to type 2 supernova, where you also see two peaks. One is called the cooling envelope. It's when the shock goes through the red giant and the outer layers cool and radiate. And The other is the plateau phase, where indeed the photosphere is controlled by recombination. But I also want to point out there's differences between type 2 supernova and mergers. One is that in mergers, in supernova, radiation pressure always greatly dominates gas pressure. In luminous red nova, they can be comparable, so you have to account for that. And the other is that supernova recombination energy doesn't matter. So recombining hydrogen is not what powers the light from a supernova. It's the energy dumped in by the shock. But in these cases, actually, the 13.6 electron volts you get per recombining hydrogen actually dominates, and that affects things. So you could take these types of simplified models, as we did with Tatsuya, and make predictions. So if you consider that the donor mass, a fraction of it is ejected, which is fixed, which is questionable, and you and then you assume it's ejected at the escape speed of the binary, then you have all the properties you need to make some analytic predictions for how luminous these red nova should be and how long their plateaus last. And so this is just showing some examples of what you get, assuming the merger occurs at on the terminal phase sequence, or maybe 10 times off of that. And so generally what you find is that brighter and longer, it's not surprising, brighter and longer transients from more massive or mergers that eject more material. And what we also found was that there was a few cases where even if we allowed the entire envelope to be ejected, it wasn't sufficient to explain their luminosities. And so this was suggested to us that there has to be some extra heating source other than just hydrogen recombination powering some of the light curves, if these are actually luminous red nova and not something else. And so a natural thing that lends itself here is that, as I mentioned, prior to the actual dynamical plunge, we have discussed there could be thermal timescale mass transfer, there could be many orbits of material which sort of create a circumstellar medium surrounding the merger. So when the material from the dynamical plunge, the fast material that's ejected, when they actually go together, goes out, it will collide with this material. And the shock actually can get hidden because the fastest ejector sort of spreads around the top, and so you can actually get shock heating, which can boost the available energy source. And so we may be seeing hints that that's present in these systems. And we know that this happens. We probably are all familiar with the example of 1309 SCO, this contact binary that was observed by Ogle for 10 years, which is the poster child for how we know luminous red nova make mergers. This was the binary where we actually see its orbital period shrinking, as well as its p dot rising. So it's merging. You can see the contact binary getting closer and closer together, and you could actually see the light curve, the phase light curve, evolve from this double peak structure where you see both sides of the binary to the end where you essentially see only a single peak. And our argument with Andre Peja is that you can understand this if you start losing mass from L2, for example, at a higher and higher rate. Eventually the amount of mass loss becomes so great that it obscures one side of the contact binary. And so it sort of takes your double peak light curve and slowly changes it to a single peak one as you lose mass at a greater and greater rate through L2. And the angular momentum loss through L2 can potentially be sufficient to cause the P dot or contribute significantly to the P dot that is observed. I want to switch gears. The problem with luminous red nova is we observe them, they're bright, and then there's this mess because there's this slow material, this dusty molecular material, it all forms dust. You can't actually see what's going on in the center for many, many years until the dust clears. So we'd like to find analogs of stellar mergers after they've evolved. I'm running out of time. So with Terry Hoadley, is a professor at Iowa now. We worked a few years ago on what we think is a stellar merger product, the so-called blue ring nebula system. And I don't know how many people have heard about this, but I'll give some shout out to it. So this was a blue ring detected by GALEX. So it's actually a biconical outflow like this. You could see the blue and red shifts as you go across this. And what you're seeing is basically fluorescing H2 that has been heated at a shock as some hydrogen-rich material has been ejected from some object in the center. It turns out in this case, you can sort of trace back how long this conical outflow to the origin. It took about 2,000 years ago, and there's at least a few hundredths of a solar mass of material in it. And there's this interesting central star in the center, PYC 2597, which has a number of peculiar properties. So it's between a 1 and a 2 solar mass star. It has an infrared excess, so it has a dusty debris disk around it. It also has UV excess. It has variable H alpha emission, which means that the star is continuing to accrete gas. These are the properties. So it's a fairly luminous star. It's a bit puffier if you compare it to, for example, horizontal branch stars. It's a bit lower surface gravity than most of them. But what's weird is it's a fairly massive star, but it's out of the galactic plane, which is where you'd expect to see older stars. So what we think is happening is that this was a 1,000-year-old stellar merger. So the same thing we described is actually similar to 1309 SCO. But there was some material which during the, let's say, merger common envelope phase was not completely ejected from the system, but remained bound in the disk and continues to this day to accrete on it. And this, but this outflow was shaped into this bipolar structure by the interaction with dense equatorial material. So one of the tests of this, we were working with the observers on this, myself and Ken Shen, and we said, well, we know one prediction of these types of common envelope events is that you heat up the star as the companion falls in, it spirals in, it heats up, perturbs the donor star, and so this star should be a little out of whack. It should still be recovering from being out of thermal equilibrium. And so we did some simple MESA models where we just dumped energy in for an inspiraling star into this 2 solar mass star with different phases after its sequence evolution, and we sort of tracked how its luminosity would then settle back onto the thermal equilibrium. And indeed, we told the observers to go, it turns out you can go back in the Harvard archival plates and look at this star 100 years ago and actually see that it was brighter and has been dimming over the last century. And so when we combined, oh yeah, I'm behind time. When we combined the requirement to explain the dimming rate, the luminosity, the effective gravity, we found that this worked pretty well if we had the inspiraling star of 0.1, 0.2 solar masses. Okay, I need to finish. What if a compact star goes into a common envelope and we have a failed? I think it's something else we think about. What happens if we have a failed common envelope event? Well, you could get potentially one explanation is you get a prompt merger between the compact object and the core of the massive star. And Sophie Schroeder, for example, has worked on this recently, that the energy released by that merger, also Noam Soker's worked on this, that energy released by that merger could basically go out and sort of effectively be like an explosion inside the common envelope ejecta, and then that could give rise to a very luminous supernova. But one thing I want to say is that, even if, let's say you do mostly eject the envelope, so the binary tightens, but not completely, and you do have some relic material left over in a circumbinary disk after a common envelope. Just want to highlight some work by my student Semi, where we looked at the long-term evolution of these post-common envelope binaries, accounting for a number of pieces of physics that I don't think were previously considered. Things like the fact that the central helium core will be a source of UV radiation, which can, it's kind of like a protostar system. You're placing the protostar with the helium core so it can photoevaporate, for example. So what we found was, not surprisingly, actually, even if 10% of the common envelope remain in the disk, it could actually cause significant evolution of the binary. Okay, my thing's gonna be taken away from me now. So, all right, I will stop by simply saying that these circumbinary disks, they may cause delayed mergers between the core and the common envelope. And I think this is interesting because it means that these mergers could happen within the environment of this relic disk. We could get explosions, and not in some big hydrogen envelope from the common envelope, but in a more tenuous, radially extended medium of this disk. And we actually do see these things called fast blue optical transients, whose time scales actually are remarkably similar to what you get if you disrupt the helium core by a compact object. So I'm going to finish there. And my takeaways are up here. I think the main one I wanted to say is that, you know, massive star binary and also lower mass, well, this is mostly massive star binary, you know, involves multiple phases of these hyperetic creatures. What I want to instill you is that there should be direct observational consequences. Even if these are rare things, they're very powerful, and they should be directly observable. And I think our local systems are a little bit biased. Okay, so I'm going to finish there. Some questions that then we'll segue into having questions from the audience that don't have to be on anything I talked about. But
yeah, so, Brian, we can also have audience questions first.
Okay.
Before we break into the discussion, and we can use that as sort of a point to transition to these questions that you have prepared. So, questions for Brian.
Should we first clap?
First, let's clap.
Very sorry for talking so long. Yeah.
Now, questions for Brian.
I have two quick questions. So I was very intrigued about the progenitors of the luminous red novae. You said they were slightly evolved stars, which kind of to me seems like we're missing the AGB stars. Can we learn something about stability of mass transfer from these systems? AKA, what does it mean that we're not seeing AGB star progenitors? Does it mean something, or is there some selection effects against them?
My guess is, well, Natasha may have her own opinion. My guess is that these ejections from common envelopes, my guess is they become dusty very quickly, and so the optical part of it is very short-lived, and then so these would be more infrared bright transients. So we may be missing them for that reason, but there could be other explanations. Maybe we don't have enough yet. I don't know. It depends on.
My other very quick question is, what if the common envelope sets in not in like the normal overflow way, but in like the tidal instability? Like what if we have like a Darwin-Riemann instability, so that your secondary star may fly into the envelope in a much more radial way, in a much more higher velocity way? How would that change? Would it change the transient itself? Like that first peak, would it be more narrow? Would it be higher? Would it be?
Yeah, I mean, I think if you ejected material very quickly, then you wouldn't have any time to sort of, you know, slowly peel off parts of the star. So it probably would, your transient would have a, you know, a very abrupt rise. I didn't show this.
It's like the plunge in would be faster, but then as you're deep in the star, I think those last little bits probably would be the same, but the initial plunge in would be shorter. Right.
And I think most of what we see with the luminous red nova is what is ejected during the initial plunge would be my guess, because these things only last for, you know, I mean, they only last for a few months. So
in their paper, which will be soon submitted, we do actually have initial blue peak. I mean, we call it as a blue because observers call it blue. It is like a 16,000, 15,000 Kelvin peak that comes directly after the plunge, and then we move to the plateau.
I had a question myself. How much, how much of the properties of the nebula is coming from the properties of the stars before merger? In a sense, can you use the properties of the nebula to say anything about the pre-merger?
When you're talking about nebula, you're talking about long-lived nebula, like from SS433?
Exactly, yeah.
I mean, my guess based on these models is that nearly 100% of the mass transferred is actually going out into this nebula. So if you can measure the mass in the nebula, my guess is that that's like an estimate of the integrated mass transfer, more or less, because a lot of these models predict that only like 1% or 10% actually gets down to the compact object at most. But what I don't know from the observers is how well you can actually measure how much mass is in the nebula, because you probably are only seeing the mass that has just been shocked. But if you could figure out like sort of the integrated amount of momentum to produce a given size, then maybe you could get a better estimate. So it would be good to get a sense from observers. But my guess is you're not going to be better than a factor of 2 or 3 or something.
That would already be nice.
What?
Factor 2 would already be nice.
Okay, okay. Yeah, we should think about it. Yeah.
As a follow-up to what Hughes just said, you could also have inefficient mass transfer before the actual onset of common envelope evolution. So you would have a fraction of the mass that was actually ejected from the system before the system actually starts the plunge in. So perhaps you could have some signature in perhaps like, I don't know, like a sort of offset on the light curve or something like that, that could be attributed to this, I don't know, like homogeneous disk or whatever that was emitted before the actual common envelope ejection.
Yeah, I mean, my guess is so these light curves turn off not because they're running out of, say, material to run into or to I mean, they mostly turn off because you're forming dust. And so the peak, if you could follow this bolometrically, it would continue in the infrared. So actually, my view is if there's ongoing shock interaction, that you might see that imprinted in heating, that is where the energy is being reprocessed by the dust. So I think it would be interesting, yeah, to get infrared. I mean, I think Roman will be very good at this, but maybe there's other things you could do from the ground. Yeah. Wise, Kishaloide has a bunch of wise candidates that I think are. Yeah.
I have a question about this kind of so-called like failed common envelope or common envelope where you don't successfully expel the entire envelope and you have a merger instead. And I'm just wondering how much we understand how much of the envelope can be removed, if any of it stays bound, if it's possible, or yeah, roughly what fraction of the envelope can be removed still, if any.
Right. So we found it was with my student semi, we found that there's a fraction that does accrete still, and then there's a fraction that gets photoevaporated from the UV, the helium core, and exactly how much angular momentum we put in the disk, that fraction, could shift. But I would say it's kind of order unity is accreted. I mean, like I wouldn't say 50-50, but it's not. You can get both matter that is unbound, photoevaporated from. So I think not all of it would end up into the black hole, say, if that's a black hole or.
Okay, thank you. So yeah, some, but not all.
Yeah, I think we need better models for if there are these disks that survive and don't get ejected. How much angular momentum do they have? Do they have the angular momentum of the original binary or something else? Yeah.
Yeah, I would like to go back again to the failed common envelope case. So the point is that according to what you're saying is that when we are supposed to have a merger, we don't really have a merger. I mean, we don't have like the black hole inside a star. We have a black hole and everything around that has been disrupted, right? That's the general overview.
I'm saying that after a common envelope, you may have the helium core or the core of the evolved star and the black hole, still orbiting each other, but there's a disk.
Yeah.
And then when they do come into contact, I don't think of it as the black hole falling into the helium core. It's actually more like it tidally disrupts it. It's a little different with a neutron star.
Okay,
it may be more relevant to think of that as falling into the helium core.
So, I mean, with neutron stars, we are still fine to look for Thorne-Chetkov objects. So it's not like it disproves the fact that there might be Thorne-Chetkov objects as well, right? For neutron stars, it behaves so differently.
That's another question. I'm not sure I believe the Thorne-Chetkov objects can survive, but okay.
Okay.
Maybe I don't want to exclude it. Yeah.
For Tizio, stay tuned for the next workshop on unstable mass transfer.
All right.
Yeah. One more quick question or comment from Harim, and then.
So you, in one of your slides, I think you showed 10% of mass loss from the merger process. I guess perhaps it's
This
from
is
the
just very
MHD?
crude. This is just very crude. I'm just saying it's closer to 10% than
Yeah.
1% or 100%.
So
I mean, it varies. I mean, you can ask people who do the simulations. This is just a rough number from this particular paper.
So I guess from the light curves of luminous red nova, you can constrain the mass lost from the merger process. Does it match this temperature?
It does. I mean, you can make it match. I will say it's very sensitive. It's very sensitive to assumptions, like whether you use the velocity that is the observed spectroscopic velocity of the transient or some estimate of the escape speed. We don't know that the observed velocity. So I would say it's reasonable. The two exceptions I highlighted were these two events, which would require larger than 100%, which to us was suggestive that there's an extra energy source, because these models assume that it's just going into vacuum. Okay, so that's the only energy source. So that was why we were motivated to think about shocks or other things going on under the surface that are adding energy. Yeah.
Right. I think we should move
okay.
on because we're actually supposed to have a group discussion and there's not too much time left. So let's thank the speaker again.
We're asking people to add questions. So what were some broader, these are some questions I raised, or we raised, Willie and I, but Matthias going, yeah, go ahead. Yeah.
Basically, the idea is that we do another group discussion like this morning. We just split up. I think we have roughly 25, 30 minutes to discuss, and then we come back and just inform everyone on what was discussed in the different groups. So here's just some ideas of questions that we came up with. But we also have Mathieu here, who will be my hand because I can't write. If anyone in the audience has other questions they want to discuss, and then we'll just add it. And the idea is to sort out this quickly because we don't have that much time. So if anyone has another urgent question, apart from the ones that are on there already that I guess you've read by now, now's the time to shout.
Do you want to read these questions out first so we're all on the same page and maybe you can editorialize a little bit?
Okay, so question one is, how do we actually spot interacting system? And now more thinking of stably interacting systems that might actually be there for a certain amount of time, especially with large upcoming surveys of different techniques. So that's question number one. Question number two is, what are sources of pre-dynamical ejecta and stellar mergers, for example, from a dynamical runaway phase or a thermal mass transfer phase preceding dynamical phase? Question number three is, what are the properties of merger products? So for example, what are their rotation rates? Are they slow or fast? What is their composition? And how can we actually, again, find those from observations? Can we tag them somehow? Are they out of thermal equilibrium? These sorts of things. Number four is, do high mass stripped stars, for example, post-common envelope, have debris disks or nebulae? Thanks. How long do they survive and are they actually detectable? And question number five is, why is the observed luminous red nova population dominated by main sequence or moderately evolved donors? That goes into one of the questions we had before. And where are the giant star common envelope events, which is what we had before. All right, so any other urgent questions that should be added to that list?
I guess, I would maybe do something like, what can we learn from observations, like by comparing two models? And like, if so, which observations? Sorry.
How I synthesize that.
You write bigger?
Okay.
From observations, and then maybe like which are the most promising of mass transferring outcomes, basically, like of this mass transferring event.
What can we learn from which observations?
Okay, anything else?
Yeah, I have one. Are the pre-dynamical ejecta
in systems that go dynamical then, and the pre-dynamical ejecta in system that remain stable the same? Or could that be the difference that causes one system to go?
Can you say that in French? Because I couldn't understand.
Is there a difference between the pre-dynamical ejecta for stuff that then goes common envelope and the ejecta in system that remains stable throughout? Or could those differences be the cause of the difference?
Could we combine question two and your question into pre-dynamical ejecta?
So the idea is just that someone from every group comes up and gives a very brief summary of what was discussed for the rest to also get a bit of an idea. I don't know if anyone made slides.
We made a slide.
You made a slide? How do we?
I didn't see where it was. Was there?
You can just bring up your laptop.
Yeah, yeah.
All right. So should we just start with question or group one? Anyone from group one? Yeah.
Yeah.
I have a plan.
You get like 3 minutes. Is that okay?
Okay.
Okay, does this work? Yeah. Right, so we were mostly theory people in group one, although we were talking about observations. So if we say something insane, you know what happened there. Okay, so the clear things that we think we should look for when we're talking about systems that are currently undergoing mass transfer. So we thought we could do Doppler tomography in closed binaries that show accretion disks. Accretion disks themselves, so if we can detect something that must be an accretion disk, then that is indicating mass transfers going on. Stream hotspots, which would show up somehow in light curves as well. So it should be like a component in there if the binaries are eclipsing. And then eclipsing binaries in general could indicate like if the period is short enough, it can indicate that these guys should be going through mass transfer because they're short enough to be interacting. Also circumbinary disks, this we're not quite sure where we would be the best place to detect them. We were thinking infrared, but I'm not sure if that's the best way to detect a circumbinary disk or not. And also nova should be super bright, so that should be visible. Dwarf nova as well, like we can look at light curves with tests or something and look at the recurrent time scales of these things. Then there's also the question, like, can we be sure just looking at a light curve that the system is a nova or not? Because a lot of them, like light curves are basically going up and down, right? So I don't know how unambiguous that would be. And then also in general, like some kind of outflow like we could see in infrared. And then this is a bit of a like cheating a little bit, but BE systems, if we look, I mean, they should be post interaction, but if you have a companion there, then they are interacting now again for the second time. So because the companion is accreting and that should be stable. So we can also look for that. And jets, I mean, if something has jets, it has to be accreting something, right? So jets. And then talking about effects of post-mass transfer, as in we're thinking, if the system just finished mass transfer, what are the things that we could look for? So this is cheating again a little bit, but like rapidly rotating things that should not be so rapidly rotating in principle. That can mean that they just went through mass transfer, stripped stars, blue stragglers, and yeah, I don't know what we wrote here.
Asynchronous.
Asynchronous, yeah, but that was like, what do
Low
we
mass
mean?
white dwarfs. Low mass white dwarfs.
Low mass white dwarfs, yeah. Yeah, and then in general, thinking of what are the observations that we want to look at. There's, of course, TESS and OGO and Plato in the future, SDSS, Apogee, and of course, Gaia. Okay, this is what we discussed. If actual observers want to say something.
Any questions or comments?
Lisa? Maybe?
Lisa, yeah, so we were looking at Lisa, and apparently there's a paper saying that if we look at the frequency of the gravitational wave, like the change of the frequency or something like that, you can tell if the system is transferring mass or not. I have no idea how that works, like how.
If the orbit
how,
is widening, then it's mass transferring.
Right. Oh, so that's great. So we can use Lisa, that's amazing.
Any other comments? All right, then we go to the second question.
Isn't will also be able to tell?
Yes, can you hear me? Yeah, I guess so. So the question was, what are sources of, well, basically pre-dynamical ejecting stellar mergers, or just in general mass loss from the binaries? And I think that if I just draw a diagram, that would be quick rather than just having to explain it all over. So if you have a Rostov overflowing progenitor here on the left, well, first of all, here on the accretor, you're going to form a disk That's, I think, well established. Well, depends on many circumstances, that's fine. One thing you can think of is the fact that the disk should lose mass where it through sort of winds. Now, the way it actually does this, that's debatable in a sense, but this could be sort of the geometry in a sense. I hope that the people on the left can see it. Okay, so that would probably produce a sort of, I don't know, polar-ish geometry for this. Otherwise, you can think of the ejecta from, well, not ejecta, but in a sense, the mass that spews away from the outer Lagrangian points. So in a way from this point over here, and also this point over here, depending if you prefer the donor or the accretor doing this. But then this would produce probably something that will remain across the orbital plane. So that's a different geometry for the material. Then, well, of course, the accretor itself could have some sort of polar outflows because of winds. I say outflows, you could say jets. And in that case, well, that has another kind of geometry per se. And am I missing something else? What? Oh, yeah. So the fact that you have mass transfer changes some things in the L over M of both the donor and the accretor. In the case of the donor, well, the luminosity can stay roughly the same, but the mass will decrease. And in doing so, L over M will increase. And so you might have that it's unstable, and perhaps you might undergo this sort of burps of mass. And if it does that, what will geometry look like? Well, again, not so sure. Maybe it will be sort of a shell, but then, you know, how will it be spherical? It's still in a binary, so maybe it will be just sort of a half shell, sort of. But the same also applies for the secondary, because the accretor in this case, the luminosity will increase, while the mass will increase, but not so much. And so you might have a similar contribution in this sense. And I think I've said all that there was to it, I hope. So.
All right, thanks a lot. Any additional comments, questions, anything?
Couldn't have been that clear.
We kind of, yeah, we're short on time.
Just one tweet.
All right. So thanks again. And let's move to question 3.
Okay, so we had identification of merger products. I wrote all these notes after the discussion, so they're a little bit haphazard. But we had, so you can get the magnetic field, I didn't know this, you can get it identified from spectral polarimetry. So this is something that you can measure fairly easily, I guess, in stars. And when you have a merger, the idea is that you become, potentially you become rapidly rotating immediately because you have all the angular momentum from the binary before the merger. In which case the new product is rapidly rotating, moves redder, spends about a thermal timescale there until it relaxes back to the blue, where it might be identified as a blue straggler. In this case, I'd asked why this is not necessarily a fast rotating system if it's kind of recompressing. And it's because the outer layers can couple either through sprout dynamo or magnetic fields. You could spin down effectively. It'll couple to the core, and then you have a slow rotator, even though it had this very large radius initially. The blue supergiants are not blue because of their composition, but because of their different structure. Their internal structure keeps them unusually blue. You might also immediately get slow rotators. This is the result from Fabian Schneider's group, that you don't necessarily keep all the angular momentum in the final product right away. Your low mass main sequence mergers may be red for, if it's on the thermal timescale, maybe 10 million years. So it might be quite hard to imagine. Well, you might actually see many of these still quite red, but also with these high magnetic fields. Unless you have magnetic field decay on, it can decay on a 10-year time scale, potentially, depending on the initial geometry. I didn't quite understand the argument, but that was something that came up. And then we discussed a little bit how you could estimate the ejecta mass of the merger from the debris disk around the circummerger debris using these density momentum arguments. Questions?
I don't know if there is any.
Comment related to it. So I was going to say, in this particular case of this central object of the blue ring nebula I talked about, it is a very bright X-ray source. So it's very X-ray active and relative to other stars. So I think these types of systems, if we can find post-merger systems that, and we can actually measure the properties and we're confident that that's what's going on, I think it's interesting. So anyway, it's just a comment. Agree.
Any other questions, comments? Yes, no, maybe? Okay, then we move to question 4.
So 4 didn't form a group, but I made a slide.
On my show. Wait, that's perfect because Katie also.
It's nice that it's organized. So.
Should be working.
Okay, do high mass strip stars have nebula or outflow? Yes, they do. So here I'm showing 2 images. These are 2D spectra. I feel like pretty much everybody in the room already knows this, but just so we're on the same page. These plots are showing wavelength on the x-axis and spatial extent on the y-axis, because when you have a shell spectrograph,
That is not a board.
Oh,
Not a board.
sorry. Over here.
Oh, that's not a board. Just throw below.
Is that a board?
That's a board.
Okay, sorry guys on that side of the room. When you have a shell spectrograph, you place a slit on top of your star and you have some of the background on either side of the star. So this is the spatial dimension I'm talking about. And when we look at some of these forbidden lines in these strip star systems, we're seeing symmetric nebulae in some of them. So a naive interpretation of this could be common envelope. And in the case of an asymmetric outflow in this system, maybe this is L2 overflow coming from these systems. So yes, we do see this.
Yay.
I actually have a question about this. I'm just going to go. When you say symmetric, you mean symmetric along one axis, right?
Yes.
You didn't flip.
Yeah. So one of the things we want to do is that because we have many epochs for these stars, you can imagine adding all of these different angles up and maybe you can get a 2-dimensional profile of what it actually looks like. So this is a very limited picture of it, but yeah, that's something we want to do.
Take an integral field spectrograph. Any other questions? Comments? All right, then let's go to question 5.
Stressed about this. Okay. Maybe. There she is. Good. Okay, so we had a group with lots of, I think, theory-focused people and some observers. So we thought about a bunch of different reasons for why we don't see specifically giant formed luminous red novae. And I think the main thing is that it could be the case that we do have them in data. It's just that they're infrared transients that don't have optical counterparts. And so if you require that they are optical counterparts to like make yourself believe that this is a thing, then you're just going to miss them always. A good potential place to start digging is the 70 or so transients that are in like this sprites catalog that came from a Spitzer survey. And there are 60 of them that don't have optical counterparts. Contamination is probably a thing that we should think about. And then we went off on a big aside where everyone yelled at Emily for being an observer for a second. And that was fine. And then we decided that probably it's the case that Roman may also be really helpful here, and that there are target of opportunity like options here. So maybe something that if people are interested, they should consider that. We also spoke for a bit of time about the idea that maybe like we know that planetary nebulae are post-common envelope systems, at least something like 30% of them. So could the non-spherically symmetric planetary nebulae like be these types of systems, but with a helium star in them? And we spent a bunch of time kind of like musing about like, oh, well, most planetary nebulae we see because there's a white dwarf that's ionizing all that gas and like lighting it up. But there are pre or protoplanetary nebulae that could be connections to like helium star style planetary nebulae. So I don't know, something to think about there. And then we got some like amazing information coming from Natasha here. So one thing that's completely bonkers to think about, and there's a bit of a brain breaker, is that if you have a failed common envelope with say a 10 solar mass donor and a 2 solar mass donor, you could imagine that the common envelope ejects the 10 solar mass donor, then there's a merger that puts 2 solar masses on top of that stripped helium core, and the star is going to continue evolving the way that it does because of the helium core, but it's just this like under massive giant star, and we don't know anything about it one way or another. So maybe this is happening. And Emily pointed out that there are observed systems that are giants that are either over or under mass for their given cluster. So maybe that's something that we should be paying attention to. We said the word astroseismic effects and everyone was like, we don't really know. Maybe we could see them though, because the relaxation of this new type of red giant would be probably faster than thermal because of the high luminosities. And then finally, just in general, we thought about general differences. And this hasn't ever been really computed with models, but in general, because you're dealing with giants, the escape velocity is likely to be slower. So the plateau will be longer and dust formation starts to become a problem that could just completely like mess everything up. That's what we said.
Any comments, questions? Or is everyone ready for the reception?
The spirit survey with it's Castival et al. I don't remember the given that they just
we'll put it in the slide.
If you want to look for the sprites, it's the spirits survey. So the Spitzer infrared transient survey, and Castival is the Mansi Castival is the first author. I forgot the year.
We'll put it in.
There's also going to be some new candidates coming out from Kishaloy Day.
Yeah.
They have a bunch of neo or wise data where they see I don't remember many more than this sprite. So yeah, this sample will be growing even with what we currently have. But it will be great to have Roman. I agree.
Good. That's what we meant by other, because we didn't have a thing to link to yet, but we're very excited.
I have a question about this 10 solar mass star with a 2 solar mass star, where you remove the envelope and then merge and you reaccrete the 2 solar mass star. And I'm wondering if this could also happen if the masses were like 10 times lower. So if you have like a 1 solar mass star plus a say 0.2 solar mass star, and if you can get the same effect or not.
That was just a vague speculation about whether it could happen. We don't have yet common envelope produced for the 10 solar mass donors in the proper way. So it was just a very, very big speculation. I mean, if one solar mass star will be able to remove an envelope from 10 solar mass giant, and then will little bit re-expand and accrete. I mean, everything could happen, right? But it, so I mean, sorry, it was just a wild speculation about a possibility, but to go to precise numbers, no. Don't quote me for that.
Well, like one with a, you said like one with a like 0.1.
Well, open wide will be just likely mixed up inside the envelope. It will be not removing the envelope.
Private communication.
It's going to be in a paper.
And I'm blamed for the rest of my life.
All right.
Five.
There were
No,
there were 5. Number 6 merged with.
No, 6 is here.
Ah, no, sorry.
Wait, is there any more questions?
There were
If there's
6
any
and
more
7,
questions on
right?
5, right?
No.
There was 6.
And Katie again?
So what I have prepared is not as neat as Katie's, but I did spend time writing it down, so I'm going to show it. Big.
Plug it in.
Okay, this is as big as it goes.
Can you make it a bit bigger?
Like command plus.
That's as big as it goes.
You hold command plus.
That's what I'm doing.
Oh, really?
Yeah. It's because the display is wrong.
The resolution is like what? Right.
Is it that? Oh yeah, that's fine.
There's a view sync to the top.
Okay. So yes, we spent a lot of time talking about LSST. That'll bring a lot of luminous red novae. And an exciting thing about this is that it might also bring pre-imaging of progenitors. So just a variety of transients. We can also learn about what type of galaxy it came from the spectra. So this is not just related to luminous red nova, but just in general from the spectra, we can gain information about how the velocity of the material, the ejecta mass. Yes, and it might be really exciting to see a remnant binary in these surveys. And a big question is how can we prepare for all of this incoming data? We also talked a bit about LISA. I'm not very familiar about on AMV CVNs, but Sylvia brought them up that they might be seen to be widening systems. And there could also be imprints of mass transfer physics on the gravitational wave background of double white dwarfs. Brian also talked about this V1309 SCO, which could be a blue straggler in the making. And then these are all just a bunch of other random things we talked about. So a very interesting thing seen in CVs is that CVs that white dwarfs in CVs are systematically more massive than single white dwarfs. So an idea might be that these low mass white dwarfs are becoming unstable and not leading into these CVs. So that could tell us a bit more about binary physics. And then, yes, I think the most interesting one out of the rest are these supernova explosions. So in addition to the huge diversity of composition features, there are also features of binary interactions pre-explosion. So I forgot the one that was mentioned, but this is the one that I remember. So trying to explain these bright supernova outbursts as super Eddington accretion onto the compact object right before the supernova happened. So this can try to bring in sort of what we expect the population of pre-supernova binaries to look like. So.
Any questions, comments? Anything to add? Okay, then Lieke, you have some practical.
First, thank all the speakers and people who put beautiful slides together and discussions together again. Okay, and thanks Julianne and Brian for leading this last hour, obviously. I have two short announcements. The first is I would love it also if all the people who made slides and discussions and summaries of those, please upload them on Slack if you want to. They're very useful resources. And then second, now we're going to the reception, which very luckily, we managed to move from this dark windowless space to the roof of the other building. The side notes are that you cannot just enter and leave that building at wish. So we all have to enter the building as a group. And I don't want people to be lagging behind. So my chair is going to lead the group and I'm going to close everyone out here and chase you away. So what's going to happen is you should all gather your stuff because you will probably not be coming back here today. Take it all the way up to the reception. We'll have drinks. You can continue your conversations there. And then, yeah, Jared?
Oh, before everyone gets up, I do have one announcement as well. So
okay, yeah. And I did want to say, so when we're up at the reception, there will be substantial hors d'oeuvre and drinks. You might still want to get food afterwards. Note that Jared and I will have to close the reception as well. So you have to be gone before Jared and I are gone. That is.
An organizer needs to remain at the reception until everyone's gone. One more announcement is that we've posted in the Slack a link to a follow-up survey to our first one. I'm curious to see how your answers change or don't. So please, let's say before the end of the coffee break tomorrow, and I'll send it in an email too, but before the end of the coffee break tomorrow, please fill that out. All right.
Okay. See you on the roof.
See you on the roof.